Right now, at this very moment, there are penguins standing on ice shelves in Antarctica, enduring temperatures of -40 degrees Fahrenheit, huddled together in groups of thousands, each bird taking turns moving from the freezing outer edges to the warm center and back again in a slow, continuous rotation that has been perfecting itself for millions of years. These birds, flightless, awkward on land, brilliantly adapted for an environment that would kill most warm-blooded creatures within minutes, are engaged in one of nature's most remarkable acts of endurance and cooperation. And in the ocean beneath that ice, other penguins are swimming at speeds up to 22 miles per hour, hunting fish and krill with an agility that rivals dolphins, holding their breath for up to 20 minutes, diving to depths of over 1,800 feet into darkness so complete that human eyes would see nothing. These are not the cute, waddling cartoon characters of popular imagination. These are supreme athletes, evolutionary marvels, survivors of some of Earth's harshest environments. And their story is far stranger and more wonderful than most people realize. Welcome. I'm glad you're here. This is a space dedicated to exploring the world's most fascinating facts in a calm, meditative way. A place where curiosity meets quietness, where profound truths become companions for drifting off. If you're new to these journeys, I'd be grateful if you'd subscribe and turn on notifications. These explorations continue because of listeners like you, and your presence here makes all the difference. Tonight, let's explore together the lives of birds that gave up the sky for the sea. Creatures that walk upright like humans, yet inhabit worlds we can barely imagine. Let's talk about penguins, not as symbols or mascots, but as they truly are. Masters of two elements, survivors of extremes, and bearers of adaptations so specialized that they reveal evolution's capacity to reshape life in radical, unexpected ways. Penguins are birds, but they cannot fly through air. Instead, they fly through water. Watch a penguin underwater and you'll see what resembles flight. Wings beating in the same motion birds use in air, body streamlined, moving with grace and speed that seem impossible for a creature so ungainly on land. This transformation from aerial to aquatic flight happened gradually over millions of years. The ancestors of penguins could fly in air, but as they adapted to marine life, natural selection favored individuals with smaller, more powerful wings better suited for swimming. Over time, these wings became flippers, solid, paddle-like structures covered in scale-like feathers, perfect for propulsion through dense seawater, but useless for aerial flight. And here's what makes this evolutionary trade-off so remarkable. Penguins sacrificed the ability to escape predators by flying, and the ability to travel vast distances through air. But in exchange, they gained access to one of Earth's richest food sources, the ocean. Antarctic waters, though freezing and seemingly barren, are extraordinarily productive. Cold water holds more dissolved oxygen and nutrients than warm water, supporting massive populations of krill, small shrimp-like crustaceans that form the base of the Antarctic food web. A single swarm of krill can contain trillions of individuals. Fish, squid, and other marine creatures feed on krill, and penguins feed on them all, harvesting the ocean's abundance with an efficiency that flight-capable birds cannot match. Which brings us to understand something fascinating about penguin diversity. When people think of penguins, they often imagine emperor penguins on Antarctic ice, the largest species, standing nearly 4 feet tall, the ones that endure the harshest winters on Earth. But there are 18 species of penguins, and they live not just in Antarctica, but throughout the southern hemisphere. Some species inhabit the temperate coasts of South America, South Africa, Australia, and New Zealand. Galapagos penguins live at the equator, swimming in tropical waters. Little blue penguins, the smallest species, stand just 16 inches tall and nest in burrows along Australian and New Zealand coastlines. This diversity reflects tens of millions of years of evolution, of radiation into different ecological niches, of adaptation to environments ranging from polar ice to subtropical beaches. And this leads to something equally remarkable about where penguins live and why. All penguin species occur in the southern hemisphere, and there's a reason for this geographic restriction. Cold, nutrient-rich currents flowing from Antarctica northward along continents create productive marine environments that support large penguin populations. The Humboldt Current along South America's west coast, the Benguela Current along southwestern Africa, the currents around Australia and New Zealand all carry cold water and nutrients northward, and penguins follow these currents. Where the currents reach, penguins thrive. Where warm tropical currents dominate, penguins cannot persist, except in the Galapagos, where unusual cold upwellings create a small pocket of suitable habitat at the equator. Consider for a moment what it means to be a warm-blooded bird in freezing water. Water conducts heat away from the body 25 times faster than air of the same temperature. A human falling into Antarctic water would die from hypothermia within minutes. Yet penguins spend hours daily swimming in water barely above freezing, maintaining body temperatures around 100 degrees Fahrenheit. How do they do this? The answer lies in multiple, overlapping adaptations that work together to minimize heat loss and maximize heat retention. First, penguins have extremely dense plumage, more feathers per square inch than almost any other bird. Emperor penguins have about 100 feathers per square inch, with multiple layers of different feather types, creating a waterproof, insulating barrier. The outer feathers are stiff and overlapping, coated with oil from a specialized gland, repelling water completely. Beneath these outer feathers are layers of downy feathers that trap air, creating insulation. A penguin's plumage is so effective that virtually no water reaches the skin, even during extended swimming. But there's more to cold adaptation than feathers. Penguins have a thick layer of subcutaneous fat, blubber, that provides additional insulation and energy storage. Blood vessels in their flippers and legs are arranged in a countercurrent heat exchange system, where warm arterial blood flowing toward the extremities runs alongside cold venous blood returning from them. Heat transfers from the warm blood to the cold blood, pre-warming the returning blood and pre-cooling the outgoing blood, minimizing heat loss to the environment. This allows penguins to maintain core body temperature while allowing their extremities to cool to near environmental temperatures, reducing the temperature gradient and thus heat loss. And here's where it gets even more interesting. Penguins can adjust their insulation by fluffing or compressing their feathers, trapping more or less air depending on conditions. On cold days, they fluff their feathers, increasing insulation. On warm days, yes, penguins can overheat, especially during exertion. They compress their feathers and may pant or hold their flippers away from their bodies to dump excess heat. This dynamic thermoregulation allows penguins to function across a range of temperatures, maintaining optimal body temperature whether standing in a blizzard or swimming vigorously in pursuit of prey. This connects to something deeper about penguin metabolism and energy use. Maintaining body temperature in extreme cold requires enormous energy. Emperor penguins during the Antarctic winter, when they're fasting while incubating eggs, can lose up to 40% of their body weight over several months. Their metabolism slows dramatically during fasting, conserving energy reserves. Heart rate drops, activity becomes minimal. They enter a state similar to torpor in some mammals, though they remain conscious and responsive. This metabolic flexibility is crucial for survival. Without the ability to dramatically reduce energy expenditure, penguins couldn't endure extended fasting periods. And alongside metabolic adaptation, there's behavioral adaptation. The huddle, groups of thousands of emperor penguins packed tightly together during winter storms, is one of nature's most remarkable examples of cooperative thermoregulation. Birds on the outside of the huddle face the worst conditions, exposed to wind and cold. But the huddle constantly rotates, each bird gradually moving from the outside toward the center, warming up, then eventually moving back toward the outside as others take their turn at the center. This rotation is self-organizing, requiring no leadership or coordination. It emerges from simple rules each bird follows, creating a collective behavior that benefits all individuals. Which brings us to the extraordinary breeding biology of emperor penguins. They breed during the Antarctic winter, the harshest season, in the harshest environment on Earth. Why? Because breeding in winter means chicks fledge in summer, when food is most abundant, giving them the best chance of survival. But this timing requires adults to endure months of darkness, extreme cold, and fasting while breeding. The female lays a single egg in May or June, then immediately returns to the sea to feed, leaving the egg with the male. The male balances the egg on his feet, covering it with a warm fold of abdominal skin called the brood pouch, and stands there, incubating, for about 65 days without eating, through the darkest, coldest part of winter. During this time, males may endure temperatures dropping to -40 degrees Fahrenheit or lower, with winds exceeding 100 miles per hour. They huddle together for warmth, moving in slow, coordinated rotation. They barely move otherwise, conserving energy. They don't eat, don't drink. They metabolize fat and protein reserves, losing weight daily. By the time the chick hatches, the male may have lost 40% of his body weight and hasn't eaten for 115 days or more, counting the time before egg laying. If the female hasn't returned by the time the chick hatches, the male can feed it a secretion from his esophagus for a few days. But if she doesn't return soon after, the chick will die, and the male must abandon it to return to the sea before he starves. But there's more to this story about emperor penguin parenting. When the female returns, having spent weeks at sea feeding, building up reserves, she finds her mate among thousands of birds through their unique calls. Each penguin has a distinctive voice, and mates recognize each other's calls even after months of separation. The female regurgitates food for the chick, and the male, finally relieved of parental duty, walks to the sea, which may be 50 to 120 kilometers away as the sea ice expands through winter, to feed for the first time in nearly 4 months. The parents then alternate, one staying with the chick while the other feeds at sea, until the chick is old enough to be left in a creche, a group of young penguins huddled together for warmth while both parents forage. Consider for a moment the navigation required for these journeys. A male emperor penguin, after fasting for months in a constantly moving huddle that may drift across the ice, must find his way across featureless ice to the ocean's edge, feed, and then return to find his mate and chick among thousands of penguins. How does he do it? The mechanisms aren't fully understood, but penguins likely use multiple cues: the sun's position, subtle variations in the ice surface, magnetic field orientation, memory of landmarks, and possibly even smell. Their ability to navigate successfully across vast, monotonous landscapes demonstrates sophisticated spatial cognition. And this leads to something equally fascinating about penguins' swimming and diving abilities. Penguins are pursuit predators. They chase down fast-moving prey in three-dimensional space underwater. Emperor penguins can dive to depths exceeding 1,800 feet and stay underwater for over 20 minutes. Smaller species don't dive as deep or as long, but all penguins are accomplished divers. Underwater, they use their flippers for propulsion, feet and tail for steering. They can accelerate rapidly, change direction quickly, and maintain sustained speeds that allow them to catch fish and squid. The physiology of deep diving is remarkable. As a penguin descends, water pressure increases enormously. At 1,800 feet, pressure is over 50 times surface pressure. This would collapse human lungs and cause nitrogen to dissolve in the blood, leading to decompression sickness if the diver ascended too quickly. Penguins avoid these problems through several adaptations. Before diving, they exhale, reducing the amount of air in their lungs and thus the amount of nitrogen available to dissolve in tissues. Their bones are solid rather than hollow, unlike most birds, which reduces buoyancy and makes diving easier, but also means they carry less air in their skeletal structure. Their muscles contain high concentrations of myoglobin, a protein that stores oxygen, allowing them to function without breathing. Their heart rate drops during dives, reducing oxygen consumption, and blood flow is redirected to essential organs, the brain, heart, while less essential tissues make do with reduced oxygen. But there's more to diving than physiology. Penguins must make decisions about how deep to dive, how long to stay down, when to ascend. These decisions involve trade-offs. Deeper dives may access more or better prey, but they require more energy, take longer, and increase predation risk from leopard seals or orcas. Penguins adjust their diving behavior based on prey availability, their own energy reserves, environmental conditions. This flexibility suggests sophisticated decision-making, not just instinctive behavior. And here's what makes penguin diving even more interesting. They sometimes engage in what researchers call porpoising. When swimming at high speed near the surface, penguins repeatedly leap out of the water, arcing through air before re-entering. This behavior reduces drag. Moving through air is easier than through water, and may also allow them to breathe without slowing down. It's energetically expensive but effective, and it creates the spectacular sight of penguins leaping and diving in coordinated groups, resembling dolphins in their fluid movement between elements. This reveals something profound about the boundary between water and air and how penguins navigate it. They are truly amphibious, equally comfortable, or perhaps equally uncomfortable, in both environments. On land, they're slow, waddling, vulnerable. In water, they're fast, agile, predatory. The transition between these states is dramatic. A penguin entering water transforms instantly from clumsy to graceful. Exiting water onto ice or rock, the transformation reverses. This duality defines their existence, lives split between two worlds, mastering each in different ways. And alongside their swimming prowess, there's their remarkable ability to find and catch prey. Penguins hunt primarily by sight, pursuing prey visually underwater. Their eyes are adapted for underwater vision, more spherical lenses that can focus in the refractive index of water. On land, they're somewhat nearsighted, but underwater their vision is excellent. They can see in low light conditions, important for deep dives where sunlight barely penetrates. Some research suggests they may also detect prey by sensing bioluminescence, the faint light produced by many marine organisms. Whether through vision alone or multiple senses combined, penguins are effective hunters, catching enough prey to sustain themselves and, during breeding, their chicks. But there's more to penguin feeding than individual hunting. Some species forage in coordinated groups, diving together, herding fish or krill into dense concentrations that make capture easier. This cooperative foraging requires some level of coordination. Individuals must dive together, maintain formation, respond to each other's movements. Whether this coordination is intentional or emerges from individuals responding to similar cues remains debated. But either way, it demonstrates that penguin behavior has social dimensions, that individuals are aware of and responsive to each other. Which brings us to the broader question of penguin intelligence and social complexity. Penguins form long-term pair bonds, often returning to the same mate year after year. They recognize mates, chicks, and potentially other colony members individually, primarily through vocalizations, but perhaps also through visual recognition. They navigate complex social environments. Breeding colonies can contain tens or hundreds of thousands of birds, distinguishing between neighbors, rivals, mates, and offspring. They make decisions about when to breed, where to nest, when to return to the colony, when to molt. These decisions are not purely instinctive. They involve assessment of conditions, learning from experience, perhaps even planning. Research on penguin cognition is relatively limited compared to studies of mammals or corvids, but evidence suggests penguins are more intelligent than often assumed. They can learn to associate specific sounds with food rewards. They show individual personality differences. Some birds are bold, others cautious. Some are aggressive, others peaceful. They appear to remember previous breeding locations and conditions, adjusting their timing or site selection based on past experience. In captivity, penguins solve simple problems, learn to recognize individual humans, and show evidence of boredom if their environments lack stimulation. And this connects to something deeper about penguin communication and vocalization. Penguins are noisy birds. Breeding colonies sound like constant cacophony. Thousands of birds calling simultaneously, each producing loud, distinctive sounds. Yet within this apparent chaos lies order. Chicks recognize their parents' calls. Mates recognize each other. Neighbors recognize each other and respond differently to neighbors versus strangers. The calls themselves are complex, sometimes containing multiple elements, frequency-modulated components, harmonic structures, temporal patterns that encode information about identity, motivation, perhaps even emotional state. And as you settle in and listen, imagine standing at the edge of an emperor penguin colony in Antarctica. The temperature is perhaps -20 degrees Fahrenheit. Wind whips snow horizontally across the ice. Thousands of penguins stand in tight huddles, barely moving, adults and chicks pressed together against the cold. The sound is overwhelming. Constant calling, a chorus of hundreds of different voices overlapping, each bird maintaining contact with mates and offspring through sound. The smell is pungent, ammonia from guano mixed with the ocean scent carried on the wind. The landscape is white and blue and gray, ice extending to the horizon, broken only by the dark forms of penguins and the distant line where ice meets sea. It's beautiful and harsh and alien, a world where life persists against odds that seem impossible. And the penguins, they're just there, living their lives, following patterns established over millions of years, enduring what must be endured, thriving in conditions that would kill most creatures, simply existing because this is what they do, what they've always done, what evolution has fitted them for perfectly. The molt is one of the most vulnerable times in a penguin's life. Once a year, every penguin must replace its entire plumage, shedding old, worn feathers and growing new ones. For most birds, molting happens gradually, a few feathers at a time, allowing them to remain insulated and waterproof throughout the process. But penguins molt catastrophically, all at once, over a period of 2 to 3 weeks. During this time, the old feathers push off as new ones grow underneath, leaving the bird looking ragged and disheveled, covered in patches of old feathers hanging loose while new feathers emerge. More critically, the penguin loses its waterproofing and insulation, making it impossible to enter the water. A molting penguin cannot swim, cannot hunt, cannot feed. It must fast, living on fat reserves built up before the molt began, standing on land or ice for weeks, waiting for the process to complete. And here's what makes molting even more challenging. The energy cost of growing new feathers is enormous. A penguin's entire plumage may weigh several pounds, and creating this much new feather material requires substantial protein and energy. Combined with the energy needed to maintain body temperature without proper insulation, molting penguins can lose 30 to 50% of their body weight. They must arrive at molt with sufficient reserves to survive weeks without eating, or they will starve before new feathers finish growing. This makes the pre-molt feeding period critical. Penguins must gorge themselves, building up fat stores, timing their return to land so that they complete molting before reserves run out. Which brings us to understand something remarkable about penguin feather structure itself. Each feather is a marvel of engineering. The shaft runs down the center, with barbs branching off on either side. From each barb, hundreds of tiny barbules branch, and these barbules have microscopic hooks that interlock with adjacent barbules, zipping the feather into a smooth, unified surface. This interlocking creates a barrier that water cannot penetrate. But penguin feathers have additional modifications. They're shorter and stiffer than most bird feathers, arranged in dense, overlapping layers, creating a surface that sheds water completely. Oil from the uropygial gland near the tail coats the feathers, adding additional waterproofing. The result is insulation so effective that a penguin can swim in freezing water for hours while maintaining internal temperature above 100 degrees Fahrenheit. This connects to something deeper about the evolution of flightlessness in penguins. Giving up aerial flight allowed dramatic changes in body structure. Bones became heavier and more solid, eliminating the air spaces that make bird skeletons lightweight. This increased density makes penguins negatively buoyant. They naturally sink rather than float, which makes diving easier, but swimming at the surface more laborious. Wings shortened and flattened, becoming rigid flippers without the flexible joints needed for flight. The breast muscles, which in flying birds power wing flapping, remained large and powerful, but were repurposed for underwater propulsion. The result is a body optimized for swimming rather than flying. Streamlined, dense, powerful, with adaptations that would make aerial flight impossible, but make underwater flight remarkably efficient. And this leads to something equally fascinating about penguin locomotion on land. They waddle. This distinctive gait, rocking from side to side with each step, appears inefficient and comical, but it's actually an energy-saving adaptation. Penguins have short legs set far back on their bodies, positioned optimally for swimming, but creating challenges for walking. The waddle allows them to swing their body weight over each foot with minimal muscular effort, using pendulum-like momentum rather than pure muscle power. Studies of penguin walking energetics have shown that waddling is actually quite efficient for their body structure. They use less energy per step than would be required for a more upright, human-like gait. But some penguins have an even more efficient method of over-ice travel: tobogganing. They lie on their bellies and push themselves forward with their feet and flippers, sliding across snow and ice with remarkable speed. This is particularly common in Antarctic species traveling long distances across ice. Tobogganing can be faster than walking and uses less energy, though it requires appropriate surface conditions, snow or ice smooth enough to allow sliding. Watching penguins toboggan creates an impression of play, of enjoyment, though whether they experience anything like human enjoyment remains unknowable. What's clear is that they've found an effective solution to the problem of moving across ice with a body designed for water. Consider for a moment the challenges of navigating ice and rock when you have flippers instead of wings and feet designed for swimming rather than walking. Penguins must climb onto ice shelves, sometimes several feet high, launching themselves from water onto ice using powerful swimming strokes that propel them upward and forward. They must navigate rocky shores with waves crashing around them, timing their exit from water to avoid being smashed against rocks. They must traverse sometimes miles of rough terrain to reach breeding sites. All of this with a body that's fundamentally aquatic, moved by flippers and webbed feet that are effective in water but clumsy on land. Yet they manage, through a combination of strength, timing, and persistence. And here's what most people don't realize about penguin breeding colonies: their social complexity and structure. Colonies aren't random gatherings, but organized communities with spatial patterns. Some species nest in dense aggregations, each pair defending a tiny territory barely large enough for the nest. Others spread out more, with greater distances between neighbors. Within colonies, there are subdivisions, groups of individuals that arrive together, breed synchronously, and interact more with each other than with distant colony members. These subdivisions may represent kin groups or social networks maintained across years. Nest sites, where species build nests, are precious resources defended vigorously. Adelie and Gentoo penguins build nests from stones, carefully arranging rocks into a raised platform that protects eggs from meltwater. Good stones are scarce, and penguins will steal stones from neighbors' nests when opportunity allows. This creates constant low-level conflict. Birds must guard their nests against thieves while also trying to improve their own nests. Some pairs are more successful than others, either through better fighting ability, better vigilance, or perhaps just better luck. Nest quality affects breeding success. Eggs in well-built, elevated nests are less likely to get waterlogged or roll away. But there's more to colony life than competition. There's also cooperation and mutual benefit. Dense nesting provides predator dilution. Any individual's offspring are less likely to be predated when surrounded by many others. Synchronous breeding means that chicks hatch around the same time, overwhelming predators with abundant prey simultaneously, rather than providing a steady supply over extended periods. Colonial breeding also facilitates information transfer. Penguins can observe where successful foragers have been and potentially follow them or search similar areas. While this information transfer may be inadvertent rather than intentional, it nonetheless benefits individuals who can exploit social information. And alongside these breeding colony dynamics, there's the phenomenon of creches, groups of young penguins gathered together while parents are away foraging. Creches form when chicks are several weeks old, large enough to thermoregulate independently, but not yet ready to go to sea. Parents leave their chicks in these groups, sometimes containing hundreds of young birds huddled together, and return periodically to feed their own chick. Chicks in creches benefit from collective warmth and from predator dilution. But they must be able to recognize their parents' calls among many adults returning to feed chicks, and parents must recognize their own chicks' begging calls among many young birds. This mutual recognition, maintained acoustically, allows the creche system to function. Which brings us to the question of predation and the threats penguins face. In the water, penguins are prey. Leopard seals are major predators of Antarctic penguins, hunting them with stealth and power. A leopard seal may wait near ice edges where penguins enter and exit the water, striking with explosive speed to grab a penguin in its jaws. Orcas also prey on penguins, though they're more commonly threats in certain areas and to certain species. Sharks and large fish take penguins in some regions. In the air, or rather from the air, skuas and other predatory birds attack eggs and chicks, swooping down to snatch unguarded young or pecking eggs until they break. Penguins have limited defenses against predators. In water, speed and agility are their best protection. They can attempt to outswim predators or evade them through rapid maneuvering. They often porpoise when entering or leaving water, perhaps to move quickly through the zone where leopard seals hunt. On land, penguins can be aggressive toward avian predators, pecking and flapping to drive them away. But they're most vulnerable when alone or when nests are unguarded. The best defense is often simply being part of a large group. Predators can only kill so many individuals, and being one among thousands reduces individual risk. But there's more to penguin survival challenges than predation. Weather can be deadly. Storms can kill eggs or chicks by chilling them or burying nests in snow. Adults caught away from shelter during severe weather may die from exposure. Food scarcity, whether from natural variation in prey abundance or from human impacts like overfishing, can cause widespread breeding failure or adult mortality. Disease outbreaks can devastate colonies, and increasingly, human activities pose threats. Pollution, climate change, habitat destruction, disturbance of breeding colonies by tourism. And this leads to something both remarkable and concerning about penguins as indicators of ocean health. Because penguins are top predators, eating fish and krill that themselves eat plankton, they're sensitive to changes in marine ecosystems. When ocean conditions change, affecting plankton productivity or distribution, effects cascade up the food web to penguins. Declining penguin populations often signal broader ecosystem problems. In the Antarctic, several penguin species have experienced significant population declines in recent decades, correlated with warming temperatures, changing sea ice dynamics, and shifts in krill populations. The relationship between sea ice and penguins is complex and species-specific. Emperor and Adelie penguins depend on sea ice for breeding. They nest on ice, and their chicks must be able to walk from nest sites to the ocean edge when they fledge. Too much sea ice makes the journey to open water too long. Too little ice can cause breeding failure if ice breaks up before chicks are ready. Sea ice also affects krill populations. Krill spawn under sea ice and feed on algae that grow on the ice's underside. Changes in sea ice extent and timing thus affect the entire Antarctic food web, with cascading effects on penguins. Climate change is altering Antarctic conditions rapidly. Temperatures are rising, particularly in the Antarctic Peninsula region. Sea ice extent and duration are changing. These changes are happening faster than penguins can adapt evolutionarily. Some colonies are declining or failing. Others are shifting their ranges, attempting to track suitable habitat as conditions change. The long-term consequences remain uncertain, but it's clear that penguins, like many species, face challenges adapting to environmental changes occurring at unprecedented speeds. Consider for a moment the evolutionary timescales on which penguins adapted to their current environments versus the timescales on which those environments are now changing. Penguins have been evolving for roughly 60 million years, slowly adapting through countless generations to the specific conditions of the Southern Ocean and its coasts. The current rapid climate change is occurring over decades, a time frame far too short for evolutionary adaptation to produce major changes in physiology or behavior. Species can adapt only so fast, and when environments change faster than adaptation can occur, populations decline or go extinct. This reveals something profound about the relationship between evolutionary time and human-caused environmental change. Evolution is powerful, but slow. It shapes species beautifully to their environments, but only when environments are relatively stable or change gradually. When humans alter environments rapidly, through climate change, habitat destruction, pollution, overfishing, we create conditions that exceed species' capacity to adapt. The result is not just individual suffering, but potential extinction, the loss of lineages that have persisted for millions of years, eliminated not by natural processes, but by human impacts occurring over decades or centuries. And alongside climate change, there's the direct impact of human fishing on penguin food sources. Krill fishing in Antarctic waters has expanded significantly. While currently regulated to supposedly sustainable levels, removing large quantities of krill from the ecosystem affects the many species, penguins, seals, whales, that depend on krill. Competition between humans and wildlife for marine resources is not unique to Antarctica. But Antarctic ecosystems are particularly vulnerable because they're relatively simple. Krill is a keystone species, and when krill populations decline, effects reverberate throughout the food web. Some penguin species face additional specific threats. African penguins, breeding along the coasts of South Africa and Namibia, have declined by more than 95% over the past century. Overfishing has removed much of the small fish they depend on. Habitat degradation has reduced suitable nesting sites. Oil spills have killed thousands of birds. Kelp gull predation on eggs and chicks has increased, as human activities provide gulls with alternative food sources, supporting higher gull populations. The combined effects of these multiple stressors have pushed African penguins to the brink. They're now critically endangered, and without intervention, they may go extinct in the wild within decades. But there's more to the conservation story than just documenting decline. Active efforts to protect and restore penguin populations are underway globally. Marine protected areas are being established to safeguard critical foraging habitats. Fishing regulations are being adjusted to reduce competition for prey species. Breeding sites are being protected from human disturbance. Artificial nest boxes are being provided where natural sites are scarce. Oil spill response protocols have been developed to clean and rehabilitate oiled penguins. These efforts have achieved some successes. Populations in some areas have stabilized or increased. But challenges remain immense, particularly those related to climate change, which requires global action beyond what any single conservation program can achieve. And here's what almost no one talks about: the economic and cultural value of penguins beyond their ecological roles. Penguin tourism generates substantial revenue in many regions. People travel to Antarctica, South Africa, New Zealand, Argentina, and other locations specifically to see penguins. This tourism creates economic incentives for conservation, making live penguins worth more than alternatives. Communities benefit economically from penguin-related tourism, creating local constituencies supporting penguin protection. This doesn't diminish penguins' intrinsic value. They matter regardless of economic considerations. But it demonstrates that protecting penguins can align with human economic interests, creating mutually beneficial outcomes. Cultural significance also matters. Penguins appear in literature, film, advertising, education. They're charismatic, widely recognized, often loved. This cultural presence creates awareness and concern that can translate into conservation support. Children who grow up loving penguins may become adults who support environmental protection. Cultural connections to wildlife are not trivial. They shape how societies relate to nature, what protections societies are willing to enact, what sacrifices societies are willing to make for conservation. And as you rest here, thoughts drifting like ice flows on slow currents, consider how much depends on tiny, almost invisible things. Krill, those small crustaceans, support penguins, seals, whales, fish, seabirds. Entire ecosystems rest on populations of creatures most people will never see. Change the krill, and everything changes. It's a reminder that nature is interconnected, that pulling one thread affects the entire tapestry, that seemingly minor changes can cascade into major consequences. Penguins, in their dependence on specific conditions and food sources, reveal these connections. They show us that conservation cannot focus on single species alone, but must address entire ecosystems, all the relationships and conditions that allow species to persist. The oldest known penguin fossil dates back approximately 62 million years, found in New Zealand, from a time just after the dinosaurs went extinct. This ancient penguin, called Waimanu manaringi, was already recognizably a penguin, flightless, adapted for swimming, living along coastlines. But it was different from modern penguins in subtle ways. Its bones suggest it was less specialized for diving, perhaps spending more time in shallow waters. Its beak structure indicates a different diet than most modern species. This fossil tells us that the penguin lineage is ancient, that these birds have been pursuing their unique lifestyle for tens of millions of years, adapting and diversifying through massive environmental changes, ice ages and warm periods, continent shifts and ocean current changes, persisting through it all. And this leads to something remarkable about penguin evolutionary history and how flight was lost. The transition from flying bird to swimming bird didn't happen suddenly. Intermediate forms existed, birds that could both fly in air and swim underwater, though probably not excelling at either. Over time, natural selection favored individuals better at swimming, even at the cost of aerial flight. Wings became shorter and stouter, better for underwater propulsion, but increasingly poor for flying. Eventually, a threshold was crossed. Wings became too small and heavy to generate sufficient lift for flight, and from that point forward, the lineage was committed to an aquatic existence. This evolutionary transition was one way. Once flight was lost, the dramatic changes in bone structure and muscle arrangement made regaining flight essentially impossible. Why would natural selection favor losing flight? The answer lies in the physics of moving through different media. Air is thin, requiring large wings and lightweight bodies for efficient flight. Water is dense, requiring powerful, compact wings and heavy bodies for efficient swimming. You cannot optimize for both simultaneously. They require contradictory adaptations. Ancestral penguins faced a choice, in evolutionary terms: remain mediocre at both air and water locomotion, or specialize for one and abandon the other. They specialized for water, and the choice proved successful. Today's penguins are among the most accomplished swimmers in the animal kingdom, even though they can't fly. Which brings us to understand something fascinating about the diversity of extinct penguin species. The fossil record reveals that many more penguin species existed in the past than survive today. Some were giants. The largest known penguin, Kumimanu baisei, stood over 5 feet tall and weighed perhaps 220 pounds, comparable to a large human adult. This massive bird lived about 60 million years ago and would have been an imposing presence on ancient shorelines. Other extinct species were smaller, some with unusual beak shapes, suggesting specialized diets now extinct. These vanished species remind us that the penguins we see today are survivors, the descendants of lineages that persisted while others went extinct. The reasons for these ancient extinctions are unclear, but they likely relate to environmental changes, competition with other marine predators, perhaps the evolution of new predators. Studying extinct penguins helps us understand the evolutionary pressures that shaped living species and provides context for current conservation challenges. If environmental changes in the past caused penguin extinctions, current rapid environmental changes could do the same. The difference is that past changes occurred over geological timescales, allowing some lineages to adapt or migrate. Current changes are happening far faster, compressed into decades rather than millennia. And this connects to something deeper about how penguins navigate their world, particularly during migrations and foraging trips. Many penguin species undertake long journeys, swimming hundreds of miles to feeding grounds, navigating back to specific breeding colonies, finding the same nest sites year after year. How do they accomplish this navigation? Multiple sensory cues likely contribute. The sun's position provides directional information. Earth's magnetic field, detectable by many birds, may help with orientation. Landmarks, islands, coastlines, underwater topography can be memorized and recognized. Ocean currents and water temperature might provide additional cues. But there's more to navigation than sensing cues. Penguins must integrate information from multiple sources, maintain course over long distances, adjust for drift caused by currents, remember specific locations. This requires cognitive sophistication, spatial memory, integration of sensory information, perhaps even something like mental maps. Research on penguin navigation is ongoing, using tracking devices that record movement patterns in detail. These studies reveal that penguins don't wander randomly, but follow specific routes, return to productive foraging areas repeatedly, and navigate with precision that suggests detailed environmental knowledge. Consider for a moment what it means to navigate across open ocean. There are no obvious landmarks, no signs or roads. The surface appears uniform, just water extending to the horizon in all directions. Yet somehow, a penguin swimming 50 or 100 miles from its colony finds its way back, arriving at the correct section of coastline, locating the correct colony among potentially several nearby. This is not simple behavior. It requires sensing subtle environmental gradients, maintaining directional heading, remembering specific locations. It's navigation comparable to what human sailors accomplish with instruments and charts, yet penguins do it with just their evolved sensory systems and brains. And alongside navigation, there's the question of how penguins find prey in the vast ocean. Fish and krill aren't uniformly distributed. They concentrate in particular areas based on water temperature, currents, upwellings that bring nutrients to the surface. Penguins must locate these productive areas, which may change location seasonally or even daily. Some researchers suggest that penguins use area-restricted searching. When they find prey, they slow down and search intensively in that area, based on the assumption that where there's one fish or krill swarm, there are likely others nearby. When prey becomes sparse, they speed up and travel to new areas. This strategy, simple but effective, is used by many predators searching for patchily distributed resources. But there's more complexity to foraging than just searching patterns. Penguins must make decisions about which prey to pursue, how long to continue hunting in an area, when to return to the colony. These decisions involve trade-offs. Spending more time foraging may yield more food, but delays return to chicks that need feeding. Diving deeper may access more or larger prey, but costs more energy and time. Foraging farther from the colony may find better prey concentrations, but requires longer travel. Each decision affects survival and reproductive success, creating selection pressure for optimal decision-making strategies. This reveals something profound about cognition in non-human animals. Penguins don't have language, don't use tools, don't build complex structures, or engage in activities we typically associate with high intelligence. Yet they navigate across featureless oceans, make complex foraging decisions, recognize individuals by voice, remember locations across years. They possess sophisticated cognitive abilities adapted to their specific ecological challenges. Intelligence, in evolutionary terms, isn't a single trait, but a collection of abilities shaped by the problems organisms need to solve. Penguin intelligence is penguin-appropriate, not like human intelligence, but no less real or impressive for being different. And this leads to something equally fascinating about penguin sleep and rest patterns. Penguins, like all birds, need sleep, but their sleep patterns are constrained by their environment and lifestyle. Penguins at sea must remain alert for predators, yet they also need rest. Studies suggest that penguins may engage in unihemispheric sleep, sleeping with one half of the brain while the other remains awake, similar to dolphins and some other marine animals. This allows rest while maintaining enough awareness to surface for breathing, watch for predators, or maintain position in a group. On land, penguins sleep more deeply, though even then, they often remain somewhat alert, waking easily if disturbed. During breeding, when one parent guards a chick while the other forages, the guarding parent must remain vigilant against predators and cannot sleep deeply for extended periods. This creates sleep debt that accumulates over days or weeks, potentially affecting health and performance. How penguins manage this sleep deprivation, whether they catch up during later rest periods, remains incompletely understood. But it's clear that penguin sleep patterns are adapted to their demanding lifestyle. Which brings us to the phenomenon of molt fasting and its extreme metabolic demands. During molt, penguins not only cannot feed, but must grow an entire new plumage, several pounds of feathers requiring substantial protein and energy. The metabolic rate during molt increases dramatically, both to fuel feather growth and to maintain body temperature with compromised insulation. Penguins can lose up to 50% of their body weight during molt. This is extreme fasting, among the most intense fasting periods of any animal. How do penguins survive such metabolic stress? Part of the answer lies in metabolic flexibility, the ability to shift fuel sources, slow non-essential processes, and tightly regulate energy expenditure. During molt, penguins metabolize fat first, preserving protein as long as possible. As fat stores deplete, they begin catabolizing muscle and other tissues. The body prioritizes maintaining critical organs, heart, brain, digestive system, while allowing less essential tissues to waste. This metabolic triage is automated, controlled by hormones and metabolic signaling, allowing penguins to survive fasting that would kill most mammals of similar size. But there's more to molt than just surviving fasting. Timing matters enormously. Penguins must complete molt before their fat reserves are exhausted, or they'll starve. But they also must time molt to fit within the annual cycle, after breeding, before the next breeding season begins, during periods when environmental conditions allow fasting on land or ice. Different species in different regions have different molt timing, all evolved to fit their particular circumstances. This timing is regulated by photoperiod, day length, and internal circannual rhythms, creating predictable annual cycles that keep the penguin's biology synchronized with environmental conditions. And alongside molt fasting, there's the related challenge of pre-molt preparation. Penguins must build up sufficient fat reserves before returning to land to molt. This requires intensive foraging, often over extended periods, eating more than needed for immediate metabolism and storing excess as fat. During this pre-molt period, penguins may double their body weight, transforming from sleek swimmers into rounded, fat-laden birds. The transformation is dramatic and essential. Arrive at molt without adequate reserves, and survival is unlikely. Consider for a moment the annual cycle of a typical penguin's life. Breeding season, lasting several months, during which the bird courts, mates, incubates eggs, and raises chicks. Then, an intensive foraging period, building up fat reserves for molt. Then molt itself, 2 to 3 weeks of fasting on land. Then, a return to sea for more foraging, building reserves for winter or the next breeding season. Then the cycle repeats. Each phase has specific demands, specific challenges, specific adaptations. The entire year is structured around these recurring phases, each bird's biology tuned to this predictable rhythm. This annual cycle is remarkably constraining. Delays at any point can cascade. If breeding extends too long, molt may start too late, leaving insufficient time to rebuild reserves before winter or the next breeding season. If foraging is poor, fat reserves may be inadequate for molt, causing mortality. If environmental conditions change, disrupting the timing of prey availability or ice conditions, the entire cycle can be thrown off. This tight coupling between biology and environment makes penguins vulnerable to changes. Their adaptations are so specific to particular conditions that altered conditions can cause system failure. And here's what most people don't realize about penguin lifespan and life history. Small species like little blue penguins may live 6 to 8 years in the wild. Larger species like emperors can live 15 to 20 years, occasionally longer. This is substantial longevity for birds of their size, comparable to many larger birds. Long lifespan allows penguins to breed multiple times over their lives, spreading reproductive effort across many years rather than concentrating it into one or a few breeding attempts. This life history strategy, delayed maturity, extended lifespan, repeated breeding, means that survival of adults is crucial for population persistence. High adult mortality, even if chick production remains high, can cause population decline because it takes years for young birds to replace lost adults. This life history creates vulnerability to certain threats. Sudden mortality events, oil spills, disease outbreaks, extreme weather killing adults, have disproportionate population impacts because they remove experienced breeders that cannot be quickly replaced. In contrast, threats that primarily affect chicks, while serious, are less likely to cause long-term population collapse because adults can breed again in subsequent years. Understanding these life history patterns is crucial for conservation. Different threats require different management responses depending on which life stages they primarily affect. And alongside life history considerations, there's the question of genetic diversity and population structure. Penguin populations are often subdivided into multiple colonies, each with potentially distinct genetic characteristics. Gene flow between colonies, movement of individuals from one colony to another, maintains genetic connectivity and allows adaptation to local conditions while preventing excessive inbreeding. However, human impacts can disrupt this structure. When colonies decline or disappear, genetic diversity is lost, and connectivity between remaining colonies may be reduced. Some penguin species have low genetic diversity, likely reflecting population bottlenecks in the past, when populations crashed and then recovered from small numbers of survivors. Low diversity makes populations potentially more vulnerable to disease, reduces capacity for evolutionary adaptation, and increases risk of inbreeding depression. Conservation genetics, studying the genetic structure of populations, helps identify which populations are most vulnerable and where conservation efforts should focus to preserve remaining diversity. Which brings us to the broader question of ecosystem roles and penguin importance beyond their individual survival. Penguins transfer nutrients and energy from marine to terrestrial environments. Their guano, excrement, contains nitrogen and phosphorus extracted from the ocean and deposited on land, fertilizing vegetation near colonies and supporting terrestrial organisms. In some areas, this nutrient transfer is substantial enough to affect soil chemistry and plant communities. When penguin populations decline, these nutrient flows decrease, potentially affecting terrestrial ecosystems in ways that extend far beyond penguins themselves. Penguins also serve as prey for various predators, forming links in food webs that connect marine and terrestrial ecosystems. Leopard seals, orcas, sharks, giant petrels, skuas, all depend partly on penguins as food. When penguin populations change, predator populations may respond, creating cascading effects through food webs. These ecological relationships mean that penguins matter not just as individual species, but as components of larger systems. Their conservation is not just about saving penguins, but about maintaining ecosystem integrity. And as you settle into deeper rest, your breathing slow and regular, your thoughts beginning to dissolve. Imagine the Southern Ocean in winter. Darkness descends, not just for night, but for months. The sun barely rises above the horizon and temperatures plummet. Ice extends outward from Antarctica, covering vast areas of ocean. In this darkness, in this cold, emperor penguins stand on the ice in their thousands, each male balancing an egg on his feet, waiting through the longest night for spring's return. They endure because they must, because their biology drives them to breed in winter so chicks will fledge in summer, because evolution has shaped them to withstand conditions that seem incompatible with life. And eventually, the sun returns. Days lengthen, ice begins to break up, and the cycle continues, as it has for millions of years, as it will continue for as long as the conditions that penguins require persist. There is a sound that emperor penguin chicks make, a high-pitched, plaintive call that carries across the ice, barely audible over the wind, yet somehow distinct enough that a parent returning from weeks at sea can identify their own chick's voice among thousands. This call is learned gradually, refined through the first weeks of life, shaped by interactions with parents until it becomes unique, an acoustic signature that will last throughout the chick's life. Every emperor penguin has a voice as distinctive as a human fingerprint, and this voice becomes the primary means by which relationships are maintained, by which parents and offspring find each other, by which the social fabric of the colony holds together across time and space.
And this leads to something remarkable about the development of young penguins from hatching to independence. A newly hatched emperor penguin chick weighs perhaps 300 grams, covered in gray down, utterly helpless, dependent on parents for warmth and food. It cannot regulate its own temperature effectively for weeks. It must be brooded, held on a parent's feet under their brood pouch, almost constantly during its first weeks of life. The parent regurgitates partially digested food directly into the chick's mouth, providing nutrition that fuels rapid growth. Within weeks, the chick grows dramatically, fed by both parents taking turns foraging at sea and returning to feed it. By the time it's several weeks old, the chick is too large to brood continuously and joins other chicks in a creche. Now it must thermoregulate independently, relying on its down for insulation, huddling with other chicks for warmth. Parents continue feeding it, but spend longer periods at sea, bringing back larger meals less frequently. The chick's growth accelerates. It may gain several kilograms over a few months, becoming rotund, storing fat that will sustain it through its first time at sea. Which brings us to understand something fascinating about the transition from chick to independent juvenile, a period called fledging. For emperor penguins, fledging occurs when the chick is about 5 months old, in December or January, Antarctic summer. By this time, the sea ice the colony stands on is beginning to break up, the ocean edge drawing closer. The chick has shed its down and grown waterproof juvenile plumage. It has been fed by parents for months, but now must learn to feed itself. The transition is abrupt. Parents stop feeding, and the chick, driven by hunger, must walk to the ocean and enter water for the first time. No one teaches the young penguin to swim. There's no training, no gradual introduction. It simply enters the water, and instinct takes over. The same flippers that were vestigial appendages on land suddenly become functional underwater. The chick dives, surfaces, dives again, learning through trial and error how to control its movements, how to catch prey, how to avoid predators. Many young penguins die during this period, predated by leopard seals waiting near ice edges, failing to catch enough prey, succumbing to the harsh conditions. But those who survive gain independence, beginning the long journey to maturity. And here's what makes penguin development even more interesting: the extended period before sexual maturity. Emperor penguins typically don't breed until they're at least 5 years old, sometimes older. During these years, they're learning, memorizing foraging locations, developing hunting skills, perhaps visiting colonies and observing breeding adults, gradually acquiring the knowledge and physical condition necessary for successful breeding. This extended adolescence is unusual for birds, but makes sense for long-lived species in demanding environments. Better to delay breeding until you're truly ready than to attempt breeding prematurely and fail. This life history pattern, delayed maturity, extended lifespan, low reproductive rate, makes penguin populations slow to recover from declines. If adult mortality increases, it takes years for juveniles to mature and replace lost breeders. If conditions remain poor for multiple years, consecutive breeding failures can cause populations to crash. Understanding these dynamics is crucial for conservation. Short-term population counts can be misleading if they don't account for age structure and recruitment rates. And this connects to something deeper about population monitoring and conservation assessment. Counting penguins seems straightforward. Go to a colony, count the birds. But reality is more complex. Colonies can contain hundreds of thousands of birds, making accurate counts difficult. Birds are constantly moving, some arriving, others leaving. Chicks are hidden under parents or obscured by weather.
Some species nest in burrows or under vegetation, making them nearly impossible to count directly. And counts at a single point in time don't reveal trends. Is the population stable, increasing, or decreasing? Modern monitoring uses multiple approaches. Satellite imagery can detect large colonies from space, tracking changes in colony size over years. Automated cameras at colonies record activity continuously, allowing researchers to assess breeding success without disturbing birds. Genetic sampling provides information about population connectivity and diversity. Tracking devices reveal foraging behavior and survival rates. Acoustic monitoring detects presence and activity patterns. These technologies, combined with traditional field observations, create comprehensive pictures of population status and trends. But there's more to conservation than monitoring. Active management is sometimes necessary. In areas where penguin habitat has been degraded, restoration efforts can help. Removing invasive predators, rats, cats, foxes introduced by humans, can dramatically improve breeding success. Creating artificial nest sites where natural sites are limited can increase colony capacity. Managing human activities, tourism, fishing, development, near colonies reduces disturbance. Rehabilitating injured or oiled penguins can save individuals, though the population-level benefits depend on how many can be successfully returned to the wild. And alongside these direct interventions, there's the challenge of addressing larger-scale threats, like climate change and overfishing. These require international cooperation, policy changes, shifts in human behavior on scales far beyond individual colonies or even nations. Marine protected areas can safeguard critical foraging habitats. Fishing regulations can reduce competition for prey. International agreements can limit emissions contributing to climate change. These broader actions are harder to implement, require sustained political will, and their benefits may take years or decades to manifest. Yet, they're essential for long-term penguin conservation. Consider for a moment the complexity of protecting a species that moves between land and sea, between territorial waters of different nations, between areas with different management regimes. A penguin might breed on one country's territory, forage in another country's exclusive economic zone, molt on a third country's shores, and migrate through international waters. No single nation can protect that penguin alone. Conservation requires cooperation across jurisdictions, coordination of policies, shared commitment to protection. This international dimension of conservation reflects the reality that ecosystems and species don't respect political boundaries. The Southern Ocean surrounding Antarctica is shared by many nations, and its resources are exploited by fishing fleets from around the world. Managing this ocean sustainably requires international agreements, like the Convention for the Conservation of Antarctic Marine Living Resources, which attempts to balance resource extraction with ecosystem protection. These agreements are imperfect, sometimes poorly enforced, subject to political tensions, but they represent recognition that shared resources require shared management. Which brings us to the question of what success looks like in penguin conservation. Is it maintaining current population sizes, allowing populations to increase, preserving genetic diversity, protecting breeding and foraging habitats, ensuring ecosystem integrity? The answer depends partly on values, what we believe is important, what we're willing to prioritize, what trade-offs we're willing to accept. But it also depends on biological realities. What population sizes are necessary for long-term viability? What genetic diversity is needed for adaptation? What habitat extent is required for ecosystem function? And here's what almost no one talks about: the emotional and psychological dimensions of conservation work. People who dedicate their lives to studying and protecting penguins develop deep connections to these birds. They witness chicks hatching, watch adults endure extreme conditions, discover dead penguins killed by oil or starvation, celebrate when populations recover. This work is simultaneously inspiring and heartbreaking. It requires sustaining hope in the face of daunting challenges, maintaining effort when success is uncertain, accepting that despite best efforts, some populations, some species, may decline or disappear.
Yet people continue this work because it matters. Because penguins matter, both for their own sake and for what they represent. They're indicators of ocean health, icons of wild places, evolutionary marvels that inspire wonder. Their persistence depends on human choices, and people choose every day to work toward their protection. This work is one small part of the larger effort to maintain biodiversity, preserve functioning ecosystems, ensure that future generations inherit a planet still rich with life's diversity. And alongside the work of conservation professionals, there's the role of broader public awareness and support. Most people will never see wild penguins, never visit Antarctica or remote island colonies. Yet public interest in penguins creates political and economic support for conservation. Documentaries showing penguin lives reach millions, creating emotional connections. Educational programs teach about penguins and their ecological importance. Citizen science projects allow people to contribute to research by analyzing images or data. This broad engagement, though indirect, matters. Conservation succeeds when societies value it, fund it, prioritize it. This reveals something profound about the relationship between knowledge, emotion, and action. Facts alone rarely motivate behavior change. People need emotional connection, to care about penguins' fate, to feel invested in their survival. Stories create this connection better than statistics. A documentary showing an emperor penguin's struggle to feed its chick resonates more powerfully than population graphs. This isn't weakness, but human nature. We're emotional, narrative-driven creatures, and effective conservation recognizes this, using stories and images to create the emotional engagement that motivates action. But emotions must be coupled with effective action. Caring about penguins without doing anything to protect them accomplishes little. Action might mean supporting conservation organizations financially, reducing personal carbon footprint to address climate change, choosing sustainable seafood to reduce fishing pressure, advocating for policies that protect marine environments, or simply educating others and spreading awareness. Individual actions may seem small, but they aggregate. Millions of people making small changes create substantial collective impact. And this connects to something deeper, about hope and agency in the face of large environmental challenges. It's easy to feel overwhelmed, to think individual actions don't matter, to despair that problems are too large for solutions. But this perspective ignores the reality that all large-scale change begins with individual choices that spread, that influence others, that eventually shift societies. Every protected area began with someone advocating for protection. Every conservation success story began with people refusing to accept decline as inevitable. Hope isn't naive optimism. It's recognition that outcomes aren't predetermined, that human choices matter, that different futures are possible, depending on what we do. Which brings us to the question of what penguins can teach us about resilience, adaptation, and survival. Penguins have persisted through enormous environmental changes over 60 million years. They've survived ice ages and warm periods, sea level changes and continental drift, the rise and fall of countless other species. Their success comes from specialization combined with enough flexibility to adjust to changing conditions. They're supremely adapted to specific lifestyles, swimming, diving, living in cold regions, yet different species have adapted these basic patterns to varied environments, from Antarctic ice to temperate coasts to tropical islands. This combination of specialization and diversity offers lessons. Overspecialization to a single narrow condition makes species vulnerable when conditions change. But too much generalization means not excelling at anything, getting out-competed by more specialized species. The sweet spot is specialized enough to excel at something, but diverse enough that some lineages can adjust to changing conditions. Penguins found this balance, specialized as aquatic hunters, but diverse in the specific ways they implement this lifestyle. Consider for a moment the parallels to human societies facing environmental change. Like penguins, we're specialized, dependent on particular resources, adapted to specific conditions, vulnerable to rapid change. But unlike penguins, we have cultural evolution operating far faster than biological evolution, allowing rapid behavioral change without waiting for genetic changes. We can innovate, plan, deliberately adjust our behaviors in response to anticipated future conditions. This capacity gives us options penguins lack. We can see problems coming and act to prevent them rather than simply adapting to whatever conditions emerge. Yet we often fail to use this capacity effectively. Despite understanding climate change and its likely consequences, global emissions continue increasing. Despite knowing that overfishing depletes marine life, commercial fishing continues extracting unsustainable quantities. Despite recognizing that habitat destruction threatens biodiversity, forests continue being cleared and coastlines developed. The gap between knowledge and action, between understanding problems and solving them, represents one of humanity's great challenges. Closing this gap requires not just individual changes, but systemic transformations in how societies function, how economies operate, how political systems make decisions. And alongside these large-scale challenges, there's the intimate, personal dimension of relationship with nature. Penguins, for most people, are distant, known through images and stories, but not directly encountered. Yet even distant relationships can be meaningful. Knowing that penguins exist, that they're out there navigating southern oceans, enduring Antarctic winters, raising chicks on remote islands. This knowledge can enrich human experience, create sense of connection to a world beyond the immediate and local. Remind us that we're part of something larger than human civilization. This connection becomes more precious as wildness diminishes. As human impacts extend globally, as fewer and fewer places remain unaffected by human activity, as more species decline or disappear, the remaining wild creatures and places become increasingly valuable. Not just ecologically, but psychologically, spiritually, aesthetically. They represent what persists despite human impacts, what remains beyond human control, what connects us to the deep past when Earth was wild and humans were small. And as you drift now into deeper rest, thoughts fading like bird calls growing distant, imagine a world still graced by penguins. Imagine coastlines where these birds come ashore in thousands, where the sound of their calls fills the air, where young birds test the water for the first time, where ancient patterns continue despite everything that changes. This world still exists, though diminished, though threatened, though uncertain how long it will persist. But it exists now, in this moment, and that existence is worth celebrating, worth protecting, worth whatever effort can be spared to ensure it continues. Tomorrow will bring its own challenges, its own decisions, its own opportunities to choose paths that either support or undermine the persistence of life's diversity. But tonight belongs to rest, to dreams, to the gentle dissolution of consciousness into sleep. And in that sleep, perhaps you'll dream of cold waters and distant shores, of birds that fly through oceans, of lives lived in ways utterly different from human experience, yet no less real, no less valuable, no less deserving of the space to continue. Rest now, knowing that across the southern hemisphere, penguins are living their lives, swimming, hunting, breeding, molting, migrating, following patterns older than human history, continuing stories that began millions of years before humans existed, and that, with care and commitment and luck, might continue millions of years into a future we can barely imagine. Their persistence is not guaranteed. Nothing's persistence is guaranteed, but it's possible. And possibility is enough to sustain hope, enough to motivate action, enough to justify the effort of protection. Sleep well, dream deeply, and may you wake tomorrow with renewed appreciation for the richness and strangeness of life on Earth, for the countless ways that evolution has shaped beings to survive and flourish, for the privilege of sharing a planet with creatures as remarkable as penguins. May that appreciation inform your choices, shape your values, and remind you that you are part of something vast and ancient and beautiful. A living world that deserves respect, protection, and wonder. Good night.